Welcome to an investigation into the very fabric of our universe. Researchers Urban Kausho, Sarah Zinn, and Janati Attai explore the quantum vacuum, suggesting that the speed of light is not just a fixed number, but a result of physical processes involving ephemeral particles appearing and disappearing constantly. In standard physics, vacuum permeability, permittivity, and the speed of light are fundamental constants. However, this study proposes they are observable parameters of the quantum vacuum. If the properties of this vacuum change across space or time, these so-called constants might actually vary as well. The vacuum is modeled as a sea of continuously appearing and disappearing charged fermion pairs, known as ephemeral particles. This includes 21 species, such as electrons, muons, and quarks. These pairs exist for a limited time, governed by an average energy and the Heisenberg uncertainty principle. Consider vacuum permeability, or μ0. The paper suggests this constant arises from the magnetization of these ephemeral fermion pairs when a magnetic field is applied. These pairs act like tiny magnets, aligning themselves and creating a paramagnetic response in what we otherwise call empty space. By calculating the magnetic moment and density of these 21 fermion species, the researchers derived a formula for permeability. Surprisingly, the calculated value matches the observed physical constant when the typical fermion is produced in a relativistic state, with an average energy about 30 times its rest mass. Next, we look at vacuum permittivity, or epsilon-0. This constant is proposed to originate from the electric polarization of these fermion pairs. Under an electric field, the positive and negative charges in each ephemeral pair separate slightly, creating a dipole moment that defines the vacuum's dielectric response. The researchers calculate that the separation between these virtual particles is roughly the reduced Compton wavelength. By summing the effects across all fermion families, the model yields the correct numerical value for permittivity, reinforcing the idea that nothingness is actually a dense, polarizable medium. Importantly, this model shows that both permeability and permittivity depend on the electric charges and the number of fermion species, rather than the total energy density of the vacuum. This contradicts common assumptions, but provides a self-consistent physical origin for the speed of light. Now, how does a photon move through this medium? The paper describes a leapfrog mechanism. As a photon travels, it is temporarily captured by an ephemeral pair. When that pair disappears, the photon is released to continue at an infinite bare velocity until it hits the next pair. These successive interactions create a delay. This renormalizes the infinite bare velocity down to a finite average speed. When the cross-section of interaction is proportional to the square of the fermion's charge, the calculated average speed matches the known speed of light perfectly. Because this capture process is statistical, the model predicts something radical: transit time fluctuations. A photon's time of flight shouldn't be perfectly constant. Instead, it should fluctuate slightly due to the random number of encounters it has with virtual pairs along its path. The variance in transit time is dominated by interactions with electron-positron pairs. The model predicts a fluctuation of approximately 0.05 femtoseconds for every square root meter of vacuum crossed. Unlike quantum gravity theories, these fluctuations are independent of the photon's energy. Scientists have looked for these effects in deep space. Observations of gamma-ray bursts and pulsars provide upper limits on these fluctuations. Currently, astrophysical data suggests the fluctuations are smaller than 0.2 to 0.3 femtoseconds per square root meter, which is consistent with the model's prediction. The paper proposes a groundbreaking laboratory test. By sending femtosecond laser pulses through a 100-meter multi-pass vacuum cavity, we could detect this broadening. After 30 round trips, a 9 femtosecond pulse would widen to 13 femtoseconds, a change detectable by modern autocorrelation measurements. In conclusion, this research suggests the unperturbed vacuum is a rich medium of virtual particles that gives birth to the speed of light. By treating vacuum as a statistical quantum environment, we gain a self-consistent explanation for the fundamental constants that govern our reality.